To już zająłem. So let's give them 1 more minute, sure. Projector went down. Making pips. Good. Right. But it was working, right? Earlier, yeah. So seeing this one, let me unplug this. It's six. Why can't I move around it very quickly? Strange. No worries. I'll move around it.
Slowly working my way towards that. More I was like topology.
So if you give me the HDMI,
Yeah. Yeah.
just stream it. Just stream it. I will just.
I see. Yeah.
W complexes. Okay. Yeah. Lots of these things really have applications with data and stuff. So I want to learn more about that and maybe
Sure. stop and start again?
No, that's fine. I mean, the problem is on my end at this time.
Take a look at some of the stuff that people do, and I try to make it like basically.
I don't have a VGA.
By doing that, I write down stuff and like from a typical theoretical point of view, and I try to look for problems where still something needed, and then I do that. Yeah.
It was out of there.
How adding some combinatorial structure to topological options.
Then just the camera.
Makes some notions more strict, but then it allows you to understand things better, do things in a more organized and structured way, and for the interface.
Almost there, almost there, almost there. On this one. Are you presenting?
I have screen sharing.
Huh?
Looks better.
Hello, that's the wall.
Sorry.
So, ladies and gentlemen, our next speaker, and let me actually properly announce for the first time, Sayan Mukherjee, very recently from Duke, now from Leipzig. So, very glad to be you in Europe. And yours.
Thank you. Thanks for the invitation, and it's been very fun to be here. So I'm going to probably run back and forth between this and that, and then we'll run some R code at some point. And the main theme that I want to kind of convey is one of the reasons why GDA and PDA have been really useful is because it really gives us a powerful way of representing data in standard methodology. So that's why I said how to represent it. Okay. So if you think about kind of data science, the classic pipeline, you first specify a problem, right? Then you design the experiment or the collection process. You have to clean or format your data, unfortunately. Then you apply some statistical, computational, numerical methodology. You want to interpret the results, provide partial answers to the questions, report findings, go back. Okay, and what I think that is really highlighted, at least from my experience, is for complex data objects or for time varying or complex data, and I'll show you what I mean by that. It really pays to think carefully about how you're going to represent your data. Okay, and this is kind of a philosophy. Most classical data analysis methods are designed for scalars, vectors, possibly matrices, right? And a lot of data formats nowadays that are not some simplicial complexes, for example, right? And for that first case of the traditional data, you have excellent stats, machine learning, numerics. So the question is, what do you do when you don't have that type of data? And what I would argue today is that there are transformations or representations of the data that really allows you to use more classical methodology in a really powerful way. Okay, so the first example I'm going to give you is not even TDA. It is model noisy count data, And I'm giving you this because it's a simple example of moving back and forth between a linear geometry and a nonlinear geometry. And it's going to highlight the examples that I state later on that involve more sophisticated shapes. So there are data sets where people are looking at a collection of microbial genes associated with the host, right? This could be something from fecal matter, it could be from your mouth, it could be from your armpit, right? There are all kinds of places. And but now people are collecting lots and lots of bacterial taxa. And you can ask questions. And this is an artificial gut. It's a bioreactor. And you can ask how quickly are changes happening? How often should we sample? What is biological change versus technical change? Right? You can start thinking about these questions. And one of the things that I want to highlight is that there's this entire process. You get your data, you're doing some chemistry, then there's some sequencing happening, then you have to assign these sequences to what taxa you think it belongs to, you denoise these, and then you get these counts. And these counts have a lot of steps that are making things noisy, right? And this is kind of just moving into a small piece of data. This is what it looks like. It's very sparse, right? If you look at it, it's a very sparse. What you have is samples by taxa, and we're looking at log of counts plus one. Okay. So some people think that these type of sequence count data are compositional. And what they mean by that is you can't really get the absolute number when you get relative frequencies. Other people think they're really counts. I'm going to start by thinking that they are compositional to show you some ideas, and then we'll get to thinking about the counts. Okay. What happens if my data lives on a simplex? Okay, that's relative data, everything adds up to one, right? So everything is living on a simplex. I just told you that. Okay, so first thing I want to say is there are two beautiful things about the multivariate normal. Right? One of the things is the notion of statistical independence in the multivariate normal is related to orthogonality. So the reason why I wanted the definition of positive semi-definite positive variance. Sigma ij is just how much, let's say, taxa I is covariant of taxa j. I can orthogonalize this, right? And those bases are orthogonal, but they also give us statistical. Okay, that holds for the multivariate normal. It doesn't hold for other distributions. The other thing is if you have a variable x and you basically push an affine transform through it, that's very easy to rewrite what that variable y is in the case of the normal. This is a tremendously useful operation if you want to write down an algorithm and do it. Okay. So this is what I'm showing. If I have these pictures, right, I look at my data, I look at one direction versus another direction, and then to project that. Another idea, which is really powerful, is let's say pre-treatment and post-treatment, I just increase or decrease one of the taxa. If things are linear, if you have an empty space, you just move it left. So far, so good. Okay. Life on the simplex is harder. Because if you move one down, what's going to happen to all the other ones? They're going to move up. Right? So you have an associated negative correlation, right? Even though that taxa might not be driving anything else, right? Because you have the constraint. Okay? And that's just what I'm showing you. Okay? So the coordinates are not independent. Same thing if I were to inject, right, one of the species up or down, you're getting these negative biases and spurious correlation. So there is a theory of what's called compositional data analysis, where they have these different views, right? That they're scaling variance. If you just pump everything up, nothing really changes. Permutation and variance, the way you order the taxa, your coordinates shouldn't really matter. And this is really tricky, which is subcompositional coherence. So if I had a data with, let's say, 20 taxa, and I added the 21st, these should be coherent, right? The bigger one should, in a way, replicate what the smaller one did, right? Okay. So there's something which is called the log ratio. And what is that? You take your counts, you take the log of it, and you normalize by the geometry. Okay? This might not be a shocking operation, right? What are you doing? You're just normalizing things on the log scale, right? That's all you're doing. Okay. Now what you can do on top of that is you can look at the simplex, which is d minus one dimensional, and you can write down the normal basis in theory. Okay, I'll tell you how to do it in a second. But in theory, you can write out a normal basis. And this is sometimes called a contrast matrix. It's d minus by d, and has this orthogonality, right, in this transformed space. Okay, and so there's something called the IOR, which is you take your CLR and you just multiply it by the spaces. Okay. Now, if you look at this and stare at it a little bit, you notice there's an exponential map here, which again should be very shocking to you, because there's a lot not coming back. There's a push forward and a pull back, as suspected. And it respects the transforms that you want. Now, what's interesting is in this case where you have microbial data, we know how they're, in a way, we know how they're related. We know what the most recent common ancestors are often. So we have this phylogeny. Okay, so far so good. If you sit down, do some annoying algebra, you can show that from this phylogeny, you can get a partition matrix stable. And the way it works here is if taxa 1 and taxa 2, right, are separated right here, then you put a +1 and a -1. And so this is looking at node. So node 2, taxa 2 and taxa 3 are separated, but at node 2, taxa 1 is not separated, right? Because it's separated earlier. And you can do the same thing up here. So node 1 is separated, taxa 1 is separated from taxa 2 and taxa 3 at node 1. Okay, so you can construct this partition matrix. From this partition matrix, you can basically construct these bases. So far, so good? Now, this is what's really neat. These are isoplines in the in your frequency space, right? And with this partition and this transformation, they turn into the Euclidean case with the Gaussian distribution. Right? Now, why am I telling you this as a statistician? It's very easy to model things that are normal. We have a ton of tools. We have very easy distributions you can work with. We have just a lot of stuff to work with. And once I transform the problem from here to here, you'll see that there's just so much more I can do. Okay. This is also neat. If I live here, and I look at exponential growth or decay, it gets mapped to straight lines with the transform. Again, probably not be shocking, right? Because it's an exponential, log, push forward, pull back. Okay. So, oh yeah, one of the things I'll do is by tomorrow, we'll post the slides and I'll add the Git directories for code that goes with this. Okay, so what you can now do is you can say I have unobserved absolute abundances, right? I don't know what they are. I map back the compositions. I have this construction that I have. And then what I can do is transform the simplex into this Euclidean space, right? Now, there's a problem with the compositional perspective. which is called log of 0. So issue, okay? So there's another idea, which is things on counts, right? These are counts. They're just really noisy counts. And that because of the design of the experiment and the way the data is structured, I don't know the absolute counts. They're very noisy. Okay. And the problem you have is, let's say system 1 you go through, and you just take a really small sample, right? This was your total, and this is what you got. In system 2, you got the same number, but it was of a bigger set, right? And so there's one thing that's always really, really, really important when you think about modeling data and statistics, which is the variance is super important, right? You just can't think of the mean. There's this great picture which shows a map of the United States, and it plots by county the rates of, I believe, if I remember right, of stomach cancer. And if you notice, if you look at this picture, the counties that have the greatest incidence of stomach cancer tend to be really remote. Anyone know why? I'll give you a hint. The counties that have the least incidence of stomach cancer are also really remote. I'm sorry?
The middle.
So why is it that the counties that are really remote have either very high incidences or very low incidences relative to other counties?
Because in some countries.
Yeah, just too few people, right? If you have so few people, you change a little bit, your variance is going to change extremely, right? And that's the same phenomena we're talking about right here. Okay. Okay, so let me ask a question. How many here are from Bayesian statistics? So maybe, okay, so maybe I'm going to spend about 4 minutes going over Bayesian statistics, and we'll come back to this picture, okay? Let's look at a really, really simple one. Let's say kind of, but I don't tell you what it is. Everyone's okay with this? Okay, so what's one kind of estimated? What's the most obvious? Anyone?
Average.
Yeah. Right, so one way we could say P hat is going to be what? Actually, let's make life even easier. Right, it's just going to be 1 over n. Now I can ask you a question. Well, okay, you gave me the average. How do I quantify the uncertainty level? Right, so this might be something you don't want to do. I'll give you a very simple way of doing it. I'm going to do a prior distribution over P, and I'm going to call it a beta distribution. There's some normalization constant, which we won't worry about. And it's going to be a P to be 1. What else is the beta? This is called uniform distribution. Okay. Now, all I need to do, so this right here is a data generating process, and sometimes it's called the likelihood. You can look at this as the likelihood of the data given parameter theta. Everyone's okay with that? Following calculation is relatively simple. The posterior is called Pn of P given data is equal to likelihood. And this quantifies your uncertainty. And in this construction, the way I set it up, this posterior will also be from the data distribution. Okay, so this is a very simple case, and you can make this much, much more complicated. And in the cases where it's much, much more complicated, all of it you have is you cannot close form compute this normalized graph. So people do Mukherjee Monte Carlo or other ideas, right? Some people are now doing really neat gradient for approaches. Okay. Our data generating process is a multinomial, right? Because these are just counts, right? Parameter of data is a point in the simplex because they're frequencies. They add to 1, right? And there's machinery to actually run this Bayesian procedure. And what we're seeing is this is your prior. We're kind of making it uniform over here. And this is one picture. And so I can start asking, how sure am I, right, about the parameter, right? We can start capturing that variance. Okay. Now, there is a distribution called the Logistic Normal, which I'll show to you in a second. It's a terrible distribution because it's got a normalization constant that's god awful. Okay, there's a distribution called the multivariate normal, which is very easy. And there is a deterministic transformation between the multivariate distribution and the parameters of a multinomial. Okay, so this right here is a logistic normal distribution. And the thing that kills it is that you have a product of your observations and denominator. Makes it very hard to work with. Okay, but what we have above and this, they're in a way equivalent. The bottom left of that model on the right is equivalent. You just added deterministic stuff. So I want to give you an example where we use this. And how many people here are familiar with what's called a Kalman filter? Okay, let me just write down a picture of the Kalman filter and we'll come back. So the idea is I want you to think about X as multivariate vector, A as a matrix, and these are my state updates in nature. They're just new. Okay. These are how the states are updated. Now we have an observation process. Let's call it y. It's going to equal data y. Let's say number. Okay. So this is a purely linear system, and this is the example of a common filter. Sometimes people make this a little bit fancier. Make them tiny. Okay, this is called dynamic event. But for simplicity now, let's just pretend, make our lives a little bit easier. So we're back to that. Okay. Now, your thetas are what I wrote down as X. This is a true biological statement. Okay, and what's happening? You have these W's, right, which are the biological variation, and it's entering or hitting your theta, right? Maybe in some linear way. Okay, and then you have your V's, which are technical ones, right? It could be that I'm looking at this bioreactor, and I a probiotic every 3 to 3 hours, and I can ask you what is happening because of the injection of the probiotic, right, versus just what's happening randomly, right? Because there's thermodynamic fluctuation and so on and so forth. And what we may want to do is we have our observations like T, and we may want to tease apart this technical variation versus this biological variation. Okay. And we go to 430, right?
That's right.
Okay. So this is getting at what I said. These are the state updates, which I have here. No, I just added back the T, right? This is kind of like the observation process a little bit. And then we pump it through this transform and then the multinomial. And what's nice about this construction is because I could use the multinomial and all of this is from normal distributions, this is very easy to implement. And you can actually scale it up reasonably large, right? But the point I'm trying to make is thinking carefully about this transformation. And so there's another important idea, which is how do we tell apart the W sub t's from the V sub t's? So if you were just to observe a time series, it would be very hard for you to tell apart the W sub t's from the V sub t's because of the design of the experiment. But if every once in a while you longitudinally sample, you can start telling things apart because the idea is in those longitudinal samples, you can get the technical variation. Okay, so that's another point that I kind of want to bring up is when we think about modeling, right? Actually thinking about how we're going to design things is also quite important. In the case of TDA, a version of this is what's your filtration going to be, right? What invariance do you want to code out, right? Mod out? What variance do you want to capture, right? And I'll come back to this. Okay. Okay, so I'm just showing you the real data. This is the yellow. The blue is a true value. Okay, and what you see is if you just look at the data, they don't overlap very well with the true value. But if you model it, you're actually getting something that's overlapping much better with the real data. This is something that's really true of a lot of time series data, which is fundamentally smoothing things helps you a lot. What else you can do, which is neat, you can start getting at the true values, basically the V's and the W's. You can start teasing those apart. Okay, I'll skip this. So yeah, so we showed that there's sub-daily dynamics, and this is one of the things that we were really interested in, is how long before the biological variation exceeds a technical variation, which gives you some idea of how often you can sample. Okay, so I'll skip this just to make things faster. This is a total model. Okay. I wanted to start with this example because it had no shape, right? It was just counts, but this idea of thinking about how you represent your data was still useful. Okay. Oh, that's a long way. So there's so one of the things that was really interesting is before Darwin, the classic perspective of looking at characterizing organism was a lineal perspective. And in the lineal perspective, people were really, really interested in platonic ideals of a duck or the platonic ideal of a chicken. I'm exaggerating a little bit, right? But this whole idea of genus was really a language we again see a lot in geometry and topology, and is really centered in this notion of a platonic ideal. And one of the geniuses of Darwin, because he thought about evolution a lot, is he started saying that what's really important is variation, right? It's not the platonic ideal, it's variation in these shapes and how that's driving the various kind of evolutionary sources, right? And this is from Beaks of Finches. And if anyone has not read A Beak of a Finch, it's a great book. Okay. Now, turns out people thought about shapes. This goes back to, I don't know, some guy named there are people who've done more recent work, right? But they're effectively kind of three ways people have studied shape. One is what's called the the shape space. And I'll show you a picture of that. But the picture of that is you go to the British National Museum and you put down 10 points on a shape. You put down 10 points in another archaeological shape. You say, I know the correspondences between these 10 points. Represent each of these 10 points as a vector in R3. And then ask, how close are they? And I'll tell you how. So that's one idea. The other idea, it's often attributed to Grenander, but there are other people who worked on similar ideas, is basically thinking about a variational flow groups, mapping one shape to another shape. And one of the ideas I'm going to talk about are using tools from integral geometry and system homology and Euler characteristics. Okay, so this is the idea of Kendall, in that you have these points, they're called landmarks. And then what do? I'm trying to minimize the squared error, modulo rotation, scalings, and translations. Right? Some people don't want to do it with scalings, but that's a different issue. But that's and this is a shape space. Okay.
So essentially, you're looking for a fine transformation.
That's right, optimal affine transformation.
So you need to have the same number of points.
You need to have the same number of points.
Yes, and if there is some non-linearity, then
You have problems.
yes.
Yeah. So it's a little bit brittle. Okay, so there's a very some say dark paper by Pearson, where a statistician who wanted to say whether what they thought the skull of Cromwell was really the skull of Cromwell, right? Which was also partially justified. And if you read this paper and you read how they did some things, I do not think they would get IRB approval nowadays, because it involved taking the heads of criminals. Okay, now on a happier note, we have very nice, rich data sets nowadays, which are stored by people, and but they are these detailed 3D meshes, right, of bones or other objects. Okay, and for those, it's very sad to take it down to a set of landmarks and transform them, right? So there's this other approach where you take observer-defined landmarks, you put little disks around them, and then you flow them from one shape to another shape, and you ask, solve that variational problem. How much does it cost to move from one shape to the other? I'll come back to this later on. Sometimes that's done using a conformal map. If these are teeth, you map it to a disk, right? If it's heel bone, you map it to a sphere, right? So yeah. So the issue with that approach is it turns out that a lot of the data sets we get are not diffeomorphic, they're not homeomorphic, right? So these are fruit flies, and then what we have below are mutant fruit flies, and they can gain veins or loads, right? So this goes back to Pavel's question, what do you do when things are not the same? So this is actually what the data look like. You have vertices, faces, and edges, right? So you really do have a simplicial complex in these data. And this is called an off file. And this is actually the data structure that these things are stored in. One data structure, I should say, which is you have a bunch of 3D coordinates. And then I tell you all the triangles. So I think we went through this, we went through this. These are bad. Okay. I'm going to give a talk later in the week where I will talk about this slide more, but for now, let's just say everything is a simplicial complex. And the only point of this slide is if we wanted to prove something and make it as general and as abstract as possible, you'd use this machine. It's a notion of tameness or measurability that logicians have developed, okay? Okay, the picture that I want to have in terms of modeling these shapes is that there's something happening on a base manifold. Maybe it's evolution. There's something that's happening in the base manifold, okay? And then what you do is you have a fiber at each of these points, and that fiber is going to represent a shape, right? And one of the things we can think about is, okay, well, in the case of Kendall, the fiber is it's a very fixed dimensional vector bundle, right? In the case of the diffeomorphisms, they're fiber bundles, right? So you can decorate them in different ways, right? And so something's happening at the organismal level down there, let's say, and then we have some representation. Okay. Okay, so I'm going to now spend a little bit of time talking about one representation. And this is a theme that comes back to the noisy counter, which is I may not have diffeomorphisms, but I want to appreciate. I want to compare them. You might want to do things like, based on the shape of a tumor, can I predict clinical outcomes, right? So I need some representation of the shape to be able to do this. And ideally, I'd like to be able to not lose information, right? Ideally, I'd like to be able to, once I do this transformation, use standard methods. And I want to be able to pull back, basically invert from that representation, right? So I can maybe make some inferences or understand what's going on. Okay. Let's see. Okay. So we're going to look at two different representations. And I'm going to focus in a little bit on an idea. So the Euler characteristic for a mesh is pretty trivial, right? It's vertices minus edges plus faces. It can also be alternating with sums of Betti numbers. And this is the idea. This is a heel bone. This is a plane. And I'm going to sweep the plane through the heel bone and look at how the Euler characteristic changes. It's called the Euler characteristic curve. And I'll do this from many directions. So if I do it in 2D with that hand, this is what it looks like. Okay? And you're basically looking at the critical points. Now, one of the things that I want to highlight is, as I go through and present different applications, we actually use different representations that are very closely related. So this was the Euler curve. This is something called the smooth Euler transform. And in some cases, we use this. In other cases, we use that. Other cases, we use persistent homology. And I'll tell you a little bit about why. Homology. This is more theory in like 3 minutes. So this gives you the diagram. Okay. So the Euler characteristic transform, if you look at it, you have your shape, you go in a direction v, go distance t, you look at the sublevel set, you compute the Euler characteristic. This is a smooth one. What's nice is you go from the sphere to function L2. So let me tell you why that. So there's an entire field, something called in statistics and parts of engineering. There's an entire field called functional data analysis. And what happens in functional data analysis is your data are functions. To be an EEG signal, right? And I'll show you how, but we have good tools to model functions. You know how to work with them. Okay. So now what we can do is just think of this, right? For each shape, you get a collection of functions, right? And so maybe somehow I could take this collection of functions, put them together, right? And make predictions of this model. And I'll show you how we do it in a second. Yeah.
How many directions will be ultimately understand this?
I will get to that. Same thing you can do with persistent homology. Okay, so this whole idea is related to something called the radon transform. So what is a radon transform? There's something called micro CT. And the idea in micro CT is, let's say I have a bone, physically a bone, and I want to get a digital version of it. Okay, so what you do is you X-ray from one direction, look at the projection, X-ray from another direction, look at the projection, right? And then what you want to do is, given all these projections, you want to reconstruct. Okay, so far so good? Okay. So this is an inverse problem, this reconstruction. The most abstract version under which this reconstruction is doable is called the inversion theorem of Pierre-Shapiro. And I will talk about this probably in more detail when I give my talk during the week. But the idea, if you look at that, is it's based on fibers and projections, coordinate projections. Okay. We and others have shown that if you take all directions, it's injective. And so this is the question. How many directions do you sample? Okay. Okay. So if anyone has not read this paper by V.I. Arnold, it's a beautiful paper where he says, if I give you critical points of a function and I ask you how many homologically different functions satisfy those critical points, he gives a closed function answer, which is kind of amazing. Okay. So I'm going to state a theorem, but then I'm going to show you a picture because I think the picture is much more useful. Okay, so if I have a moduli space of shapes, it's embedded in RD. There's some notion of minimal curvature at each point. And for that, if I construct a cone with that minimal curvature and ask how often can critical points change along that cone, basically I need a bound on it. So what am I telling you? The thing's not too flat because it's really hard to tell apart two things that are flat. It's really, really hard. And it's tame in any cone. So you can get a bound. But so this answers your question. But there's something, shoot, I think I made a mistake. I'm going to stop sharing because there's a picture I really want to show you guys. Okay, this will work. Come on. Great. Sorry about that. Here we go. Let me get back to sharing. So this is a picture that I really want to highlight. So this is actually what's happening physically, but it's also what's happening mathematically. We go sweep in a direction, okay? And let's say we compute the Euler curve right at that orange point, okay? And that's what it looks like. If I move to a cone nearby, there's going to be a linear relation between that orange point and a new orange point. So basically what's happening in terms of the tameness and the flatness is you're stratifying the sphere into little cups, right? And so if you actually thought about it in terms of the radon transform, before you did the inversion, local projections are almost linear, right? So you have things that are locally linear before the inversion, and then when you patch them, right, they're not locally linear because they're a shape. Okay, so there are many ways of thinking about this. One is that can we characterize something by just taking random projections, right? Which people actually do in high dimensional data analysis, right? But then there's also the idea that maybe we shouldn't have even, I mean, in terms of the data analysis, maybe we should have not looked at the shape, right? Maybe we should have looked at those local projections as our raw primitive, right? Because basically I'm just undoing, right, the radon transform. Okay. So I told you that. Okay, great. Now we can stop sharing. Okay. Oh no, that's the wrong one. No sheaves. No sheaves. We do not want to do sheaves. Okay, great. Okay, great. We're getting here. Okay, so I'm just going to show you one of the original results we got, which are, we have 106 primates, heel bones, and we wanted to see how similar they are. Some of these are extinct, some of them are extant. So in this, we took the persistent homology transform, looked at the W2 Wasserstein metric, and computed how similar they were. That gave us this distance matrix, which is 106 by 106. We ran a procedure called multi-dimensional scaling, which embedded it basically into 2D, right? And you have the great apes up top. Gibbon is a lesser ape. Spider is a spider monkey. And so basically you can start partitioning things up into old world monkeys, new world monkeys. There are some errors, and as well as things like tarsus and eyes, right? These are things that live in Madagascar. Okay, and so you can.
So you recover geography from the shape of the
You go recover geography. You're also recovering evolutionary history from the shape of these, right? So this is kind of interesting, and this is just pictures of using the persistent homology transform, the continuous. Okay, so this is a diffeomorphic based approach, and up top is a landmark based approach. So there's a very basic question though that this raises, which is when you have non-diffeomorphic shapes, what is the right mathematical way of comparing it? Right? You probably don't want to do like Gromov-Hausdorff, because you can try, may not work well for you, right? But how do you think about that? And there's some very nice work by Hadwiger thinking about versions of this, but this is an interesting question. Okay.
Is related to the adaptation or it's not?
What is?
Which is the right method?
Yes and no. So we found that the persistent homology transform did better than other methods, including the Euler characteristic transform. It has a bit more stability built into it. The question that arises is if someone asks me what's the gold standard of the distances between these, it's a little bit harder for me to say. Here, actually, I'm lying, because these are all diffeomorphic, it turns out. But I have a colleague at the Museum of Natural History in London, and she has all these skulls, and the skulls are really, really not diffeomorphic, right? So, yeah, of animals. I'm sorry, of animals.
I have one.
Yes.
In the previous slide, we have these three they were like different projections or different directions of people.
So these are doing multidimensional scaling to get the points, and then coloring them in with respect to the taxa and filling in the faces to make things look pretty. So we took the,
last part, the first part.
so we took the,
Why there are three? Because you choose a different filtration of the
why are there 3 dimensions or why are there 3 colors?
So what is the difference?
Oh, okay, sorry. So B is using the persistent homology transform to get the distances. A is by putting down a set of landmarks and using those with the Procrustes method. And then A is using a diffeomorphism-based approach where we're using a conformal map to flow from one object to the other and looking at that variational distance as our metric. Okay, so this is a brain, and this is a glioblastoma, and this is a section of glioblastoma. And there are 92 patients. We have gene expression data. These morphometric features are features that what are they called? Radiologists and oncologists came up with. And the volumetric features aren't, they're really stupid. And the topological features are basically doing a variation of the Euler characteristic transform. And we tried to predict disease-free survival and overall survival. So this is just a picture. You take a slice of the MRI, and then you go through different directions, and you get the smooth Euler characteristic transform. So far, so good? Okay. How many people here know about Gaussian process regression? Okay, so we're going to spend a little bit of time doing Gaussian process regression, and we'll also play around a little bit on RStudio, and then we'll come back and we'll apply that very idea to predicting outcomes of tumors. Okay. So there was once a world pre-deep neural networks. And the methodology that I'm going to be telling you about was probably the best nonlinear regression method back in those days. It's still pretty good. Sometimes it does better than some deep neural networks, but often deep neural networks do better. The idea is something called Gaussian process. Okay. So first thing is you have something called Gaussian process. Okay. Let's say it's indexed over an, let's say, to make our life, so let's just index it over the unit interval. Look by that. Okay, so I'm gonna write some short form. The basic idea behind the Gaussian process is that for This is called the covariance. It's a covariance of, let's say, a function. At the value of pi, at the value of j. An example of this would be into the mind. You just have points close by or correlated. And what's really, really nice about this is you're defining something on an infinite dimensional space by its finite dimensional projections. Right? I never told you what the process is, right? Over the entire level of 0, 1. I just told you for any finite dimensional projection, right, onto a set of points, it's multivariable.
They're essentially approximating the unknown function of a mixture of motions.
That's, yeah, you can think of it that way, yeah, with a little bump of each, right? And what's nice about this is it's actually random. This is a random process. It's not a function, but it's a collection. So far, so good. So now, what we're going to do, and I'm going to show you some pictures of this. Let's say I have, okay, let's say I have y, right? Let's say we're in the regression scheme. X I on y I is equal to 1. Everyone's okay? And let's say I have some notion of loss. So I have some notion. So I say y I is equal to some function f of x I, what it is, plus epsilon I, epsilon I t. Right? So f is some non-linear function. So let's say now I can fire with f. I tell you it's drawn in the Gaussian process. Let's just say mu 0 and some covariance. For example, let's say KP. So far, so good.
I don't have my glasses.
No problem. So far, so good. Okay. So let's say these are my training data. Let's say there's another set of points. Let's call it x sub j. J equals y. We have the money things. I don't bring y points. Right? I only have the x's. So far, so good. So what I might be interested in is f x star. So I might be interested in learning this function, right? I know x and y, right? X star. Right, and let's say there's a y star, which I don't have. Right? So what you can do is, because everything is multivariate normal, you can ask the question of, there's another one. I want to get this f star. Right? I have these x and y, so I know what these values are. Right? And these are my unknown things. So basically, you can put conditioning to get f star given x comma y comma x star. Okay. And it's just that formula there, which I wrote out, which is I want to know these f stars. I know x star, I know x, I know y, right? This has to be multivariate normal because everything is multivariate normal here. And if you just do kind of just classic multivariate normal theory, this is the covariance evaluated at all the data points that had y's associated with them, plus some noise. This is at the unknown points by the known points. And then this is the covariance matrix, sigma star. Okay, so we're going to use this idea to take those vectors we get from the Euler characteristic to try to predict disease outcome. Okay, but before we do that, I wanted to show you something. So, oh, I have to share my screen. So let's, hopefully this works. Okay. So what I'm doing here is just plotting the prior. Right? We have a very particular type of kernel. If you look at the code, it's just writing out what that covariance matrix is going to be at a ton of points, right? And it's just randomly drawing functions from the prior and basically giving you the realization, right? And I think they should be zero mean because I think I made them zero, right? So that was my prior. Okay. So now let's. So if you now see F stars, right? Let's stop here. Okay. So now what you're seeing is what the posterior looks like. So there were 1, 2, 3, 4, 5 data points that we put in, right? I made the wildly inaccurate statement that there's no noise, right? That's why you have a perfect fit at the data points, right? And what you see is as I move away from the data points, you get more uncertainty. And that also has to do with the curvature, how close things are, so on and so forth, right? So you're getting a fit and you're also getting some notion of uncertainty. And as you see, extrapolation is a lot more noisy than interpolation. Okay, so far so good?
And do you have any explanation why you are getting much fewer noise between the first 2 points than between number 3, 4, and 5?
So these 2 points are not getting much noise because it's almost so linear.
Okay.
Right, so they're very nicely kind of fitting on top of each other.
But
Whereas
the other two is also almost linear when you go down.
when you go down here, yeah, I don't know. Good question. And so now what we'll do is now if you look at it, there's a little bit of noise. Right? I had just added some noise at each of the values of that, right? So I said, you know, at the known values are not predicted exactly. Okay, and so this is the idea of Gaussian process regression. Okay. Okay. So I can now make prediction. Now the question is, what is my covariance structure? What should this covariance kernel be? So we'll do one that's really simple. It's just a correlation. How correlated are two curves? That's a linear one. Then you can look at distance-based ones. One could be something that looks like a Gaussian. Another could be something with a heavier tail. Okay? And you run all of these. And what's interesting is, in general, topological features are doing the best. We were a little bit surprised about this, and we're actually extending this now because glioblastoma may not be the best example of where you want to do this, because if you have a glioblastoma, chances are pretty high it's not going to go well. But there are other brain cancers, for example, gliomas, which often have very good prognosis. So what people are trying to do is something called radiogenomics, where you just image the person semi-regularly and don't give them a lot of chemo. And then if you see something going bad, then you're much more aggressive, right? But you hope that the kind of tumor just doesn't really increase very much, right? So we're actually involved in a study doing that. Okay. Okay, so one of the things that we did recently, which I think I was really excited about, is pushing a little this regression idea a little bit further. So what happens if you don't want to just make a prediction, but want to understand what parts of the images are most variable? So let's say we have, I don't know, two types of molars. Maybe some of these are from fruit-eating lemurs, and the other ones are from insect-eating lemurs. Okay. Can we tell you that given these two, what physical locations in 3 space are the most different? Okay. So what you can do, and here so in the previous example, you saw we used a smooth Euler characteristic transform. Here we did not. It worked very badly because it was smoothing things too much. And I'll show you why. Here, the Euler characteristic transform was much better. So what are we doing? We're sweeping through by looking at the Euler characteristic transform. And then we can use, I'll tell you more how to do this, variable selection techniques in statistics to tell you in which direction and at what depth, right, at what height, do these curves look the most different between the two classes? Okay, and those are the things that are encoded in red. So far, so good. And then basically, it turns out if you tell me the direction and if you tell me the height, I can do a little bit of projective geometry to get an estimate of what the 3 coordinates are, x, y, and z, right? And so that gives us the inverse. And this is a false color map in red of the parts that are most different. And again, this is using, yeah. So there's another idea that that you see a lot in statistical modeling, which is, and this is coming up a lot more. There are people who are very modular oriented, and there's a long tradition of this in AI. There's a long tradition of this in more CS approaches to data analysis, because you really want to break things up into modules, and you want to have decent version for each module. But the idea is if you have things in modules, you can swap things out. It's in a way, coding-wise, data structure-wise, more efficient. Among more classical statisticians, they don't like modules. There's this very much feeling that you want to model from start to end and kind of put it all together. Right, and I think that there's something to be said for both, but going forward, I think having some modularity just practically is often really helpful. So you need some way of representing shapes. Okay, you need some way to classify them, right? So I told you that. So what we do is we solve a regression problem. It's a nonlinear regression problem. And I won't torture you with the details, but we have a way, well, I can if you want. We have a way of getting, for nonlinear functions, basically estimating what those betas are, what the effects are, right? And the short answer of how we do it is it's called linearization. But we'll come back to that. And so then we project onto those. Okay, now there's one thing that's important. If you notice, everything you see here is effectively linear, right? Because you have a Gaussian. I'm just manipulating Gaussians. I have some steps where I have to do something a little bit more fancy, but it's really just manipulating Gaussian. And everything is linear. And what's nice is because I'm doing a Markov chain approach, I just don't get one beta. I get a lot of draws of beta. Let me write this down. So you go. Right, so I have some notion of uncertainty because I've sampled and I've collected all of these. So far, so good. So now I want to tell you that some subset of these betas are the most relevant. Okay. So this is this notion of centrality, which is a very simple idea. You have a team, you get rid of one player, you see how many wins they get, right? How much does it change, right? And so in the context of our Gaussians, I can take these. You know what? I'll make an assumption, which is probably not true, but I'll assume they're normal. Just assume that all these betas are normal. And so now I can think of distribution on betas, right, as multivariate normal. It's going to be some mu and some sigma. That's okay with that? So now what I can do is, because I have that structure, I can compare what happens when I take out the jth coordinate versus I integrate out the jth coordinate, marginalize it, right? And I can look at how much that changes. And that tells me in a way how relevant that jth coordinate is. Okay, and then I normalize it. And this is what we call rate. And this is how we rank each direction and height. Okay. And so the way we do the reconstruction of the 3D points is really based upon that capping idea. I told you that things are nice locally, and so there's a little cap. So if you know what direction and how deep, if you run a little cone right around there and then kind of look at how that cone hits, you can recover. So that's effectively how that worked. Okay. So what was really interesting or fun is how do you validate it? Right? How do you do simulations? Right? So what you can do in this case, which is really fun, is you can take a tube and you can go find code that the computational geometers have met to capture the shapes. You can like elongate, cusps and play around with that. And so we did that to try to validate some of this stuff, and I'll just skip through that. So this was another example where we had to adjust slightly what we were doing. And so let me show you this example. So you know how we were trying to tell apart, one class of teeth, let's say, from another class of teeth? And actually, one of the things that was interesting when we posted that previous paper about subshape selection, some people from Genentech sent us an email saying that they started using it for psychoactive medicines. But can you do something similar with protein structure? So people do molecular dynamic simulation, and you get 3D coordinates of all of these atoms, right? And they build pictures like this, so they fill it in with what the actual atoms are. And then from that, they get what these called ribbon diagrams, which is more detailed structure. Okay. So what do? You have these input protein structures, and then we create a 3D mesh representation. Fill it out really like you're doing something a little bit like persistence, And then we sweep through it and collect these topological summaries. Now, if you notice here, we don't use the same type of Euler characteristic transform. We use a slightly different transform because in the case of the protein structure, things are not always so smooth. You have jumps, right? So again, you have to think about what is the variation you're doing. We again do the similar idea to highlight. There's cones and angles, you come back and you put planar projections, and then you come back and make these ribbon diagrams on the parts of the linear system, right? So again, this is adapting what we were doing, right? And thinking about a slightly different model. Again, thinking a lot about representation. Okay. There are two other examples I kind of want to get through, and then maybe we could have a conversation a little bit about thinking about modeling and thinking about some of these approaches. One is, what happens if you don't have shapes or surfaces? What happens if you have a field? If you have soft tissue or MRI, right? What can you do? And there's a very simple idea here, which is called the lifted Euler characteristic transform. So now what you do, and this goes back to a classical idea of thinking about the Euler characteristic came from people studying random fields, right? Part of the application was asking, is a universe Gaussian, right? If it's not, then you can say there's some interesting you can say in cosmology, right? So what they did was they took random fields and they filtered according to their functional values, right, of the field, like extremes versus smallest, and they worked out an entire theory of what those filtrations look like, right? And this was done a lot by, well, one of the more applied people was Keith Worsley, and then more of the theory was done by Robert Adler and Jonathan Taylor. So this idea of filtering by function value was in the literature, right? So all we did is we said filter by the function value as well as a direction, right? As well as a height. So now what do you get? Instead of getting a vector, you're almost getting a matrix. And then you just do the same thing in a way that I told you before. To that matrix, you can define inner products on it. And we applied this to a breast cancer classification problem. It did okay. It did okay. Its competitor was a very, very highly tuned deep neural net, which, you know, took a lot of time to tune. But again, the point being is that with simple representation, sometimes you can get kind of quite far, and then you can think about it, right? But so what I showed you is for fields, there's a simple transformation, right? Just lifting it. So there are other types of lifting arguments, right? If you go from a field, I'll give you a really interesting example. There's a type of modality where with each voxel, at each point in 3D, you're getting a matrix. And you're getting a matrix of how oxygen in a way is spinning, right? So now one question is, can you adapt that? Can you lift onto SO3, right? So this is, you know, thinking about this representation, there are a lot of things you can do. So I'm going to close with something which we started and never finished. And thank you. I'd be really interested in finishing this, which is the following. And we'll come back to this picture of a base manifold and a fiber. Okay, and what I have in the base manifold is just some standard evolutionary process. And I'll show you what I mean by that. And then what I can do is conditioned on what's happening on the base manifold, I can put a Gaussian process on the fiber. Okay, so the base manifold, here's an example of something called the Ornstein-Uhlenbeck process. And it's a diffusion with a drift term. And for that, you can actually define a kernel. And it depends on the most recent common ancestor and the amount of time historically that it's had. Now, this is a commutative diagram of a fiber bundle. If I look at this as an applied probabilist, it tells me things are independent, conditioning on the base, right? So what I can do is I can define a distance, which is the cost of the map from the left to the right. And here I'm doing it in terms of some type of diffeomorphism. Sometimes they're conformal maps, okay? And so I can define this fiber in terms of this distance, product it with respect to what's happening evolutionary, right? Because it's a fiber, you can product it. And then what you can ask, so there's another point here, which is important. There are people, including me a long time, a while ago, and including here, that have said things that are mathematically incorrect. So I'll tell you why what I said here is mathematically incorrect. This, in general, is not positive definite. So there's a theorem that says, if I take a Gaussian process on a manifold, and I construct it in the following way, define that kernel of a similarity as e to the minus some positive constant times the geodesic, right? That is only strictly positive definite if that manifold is isometric to Euclidean space. And if it were, why would you even do this, right? So, so how do you generalize that? Now, we empirically saw that. We saw we got some small negative eigenvalues. We did the practical thing. We truncated them and went on with our lives. But the correct thing to do is to solve that stochastic PDE, right? So you have the Laplace-Beltrami operator, you have your Gaussian, and you solve that PDE to get the geodesic, and that is positive definite. And you can pick different operators there and get different types of kernels. So that's quote unquote the correct thing to do, but it's a little bit more work.
So is it equivalent? Because with Laplace-Beltrami operator, you can actually take the embeddings of abstract metric spaces into Euclidean. So is it doing it actually optimally, and then you do this your stuff?
That's right. That's exactly it. That's exactly right. Okay. So one of the things we're very interested in is if I have two evolutionary models, let's say Brownian motion and Lorentz-Dinolenberg, or Brownian motion and something called a burst model, can I integrate out the fiber structure, right, and see whether I have more evidence for one versus the other, right? And again, this is something that we're working on right now. And there's one last thing I want to tell you, and then I think maybe we can talk a little bit. And this is an interesting. This is a field ball. Another field ball. Another. Let's say I morph from here to here. I morph from here to here. I morph from here to here. I don't get the identity, right? Because it's data, it's noisy. You don't get the identity. So there are a few questions that this raises. One is, can we design stochastic processes, right, that add proportion as we go along, right, that add these little steps? So that's one question. The other question is, maybe we can think about this one. Maybe we shouldn't think about things in terms of exact correspondences. And these maps are random. These maps are stochastic processes themselves, right? And the way we should characterize this is in terms of these compositions of these stochastic processes. And that's how we model things, and that's how we think about our similarities, and that's how we think about answering the questions as we go further out. Right? So that's an open question. Right? How do you think about it? Think about it holistically or stochastically? Right? So I think that's another kind of question that I think is pretty interesting. Now there's.
So if I have a practical question regarding the picture which you just raised, So they take three identical, no, that's fine. They take three identical objects and start to look at stochastic maps and start to compose them. Can you actually able, by looking at some sort of structure of the map, to say that those objects are really the same or isomorphic or isometric or iso something?
So I guess this is a question: is if I iterate these maps, right? So let me actually draw. Let me actually see something. There's a beautiful literature on lifting ground and motion onto manifolds. One of the better summaries is by this person named Mukherjee, but it goes back to Algebra and it goes back to people like Ellsworth. And the idea is that there are two types of you have a basic lift, and then you lift. And there are two types of lift. There's a vertical lift, right, which is kind of the representation, and then there's a horizontal lift, which is kind of your correspondence. But now what you can ask, which Pavel has actually just asked, is if these correspondence steps, if these horizontal are random, right? If I iterate like a walk or something like that, an expectation, do I get back the true identity correspondence? And I don't know the answer. That's again open. As far as I know. Okay. Okay. So I think this idea, I'll actually start, and can talk a little bit, is of how we really think about representing our data in a way that it's flexible, lets you use more standard procedures, right? Again, I think it's really worth it because it can save you a lot of trouble, right? If you have a nice representation that's easy to work with and is in a way the push forwards and the pullbacks are somewhat manageable, it really gives you a lot. The other thing is, if you noticed, as I went through the different applications, I had a problem with them. So when I was classifying, I didn't really care about what the features were. We just wanted something and then classify, right? And then later on, when we were interested in the 3D structures, we really went more after that, right? And so a lot of these modeling problems, I mean, I think this goes from kind of classical modeling and applied math to statistics. You really want to somewhat be problem specific in terms of what you're doing and how you're thinking about this. So yeah, with that, I know we still have like 25 minutes, but maybe we can have a discussion. So let me start. As someone here, is there a particular type of data or data set you've looked at that doesn't look horribly nice?
Yeah, I do, but that's not a question to me, right?
That's not a question to you. Anyone else? Okay, so one thing you saw, right, is we were looking at these level sets to try to understand something, right, about data. Let's say you're an algebraic geometer and your data is a polynomial, right? Can you use something similar to characterize properties of the polynomial?
What properties of polynomial are you referring to?
Well, the kind of density of the extrema, or how the critical structure is changing, right? And how much information does that give you?
Because we are speaking about multivariate.
Speaking of right, so again, don't know.
What are the government bases?
Huh?
The government bases in the period.
So at least maybe I convinced you that sometimes doing statistics is useful. And maybe I convinced you that the variance is a good thing to look at. And you might want to consider uncertainty, right? There are other really interesting ideas that are showing up right now in statistics and machine learning that are using properties of metric spaces. People are really using Wasserstein gradients to generate and train things about neural networks, and using them in ways that are, scientifically useful. And other people are doing things that are mathematically, non-stupid, right? So it's, there are interesting things that are happening.
So let's just say using Wasserstein. Are we speaking about distances between distributions or point
Yeah,
clouds?
between distributions, some point clouds as well, but a lot of distributions.
How to define derivative? Because you need it for the gradient descent in the background.
So yeah, right. So one version of this is, and this is a paper where people wanted to sample from some distribution, right? Pi e to the minus v. Okay. And what they said, okay, I want to sample from this, but I don't really know how. So what I'm going to really worry about is the collection of the means. Let's say it's an RD, the distributions in RD. I'm worried about the means and the covariance, right? So if I get those right, I'm happy enough with my uncertainty quantification. If things aren't multimodal, you're okay.
I can estimate it from something.
Right, but you can actually closed form right out the flows, right? So yeah.
So why to do it in the first place?
So why to do it is,
Let's not misunderstand your point, but if you give me a sample, I can estimate the median, I can estimate the covariance.
right, but I don't have a sample. I'm
Ah,
trying to sample.
Sorry.
Yeah. I'm trying to sample, right? So there are examples like that. The people who are trying to, given data, generate noisy data, right? New versions, right? And they're using, they're doing things like that. So yeah. But anyways, what I think is there's a lot to do in TDA. And there's a lot to do linking more these representations and how we think about them with the math, right? And the statistical model. There's a lot more to do. And I think if someone's a good mathematician and they spend just a little bit of time thinking about the statistical modeling, you can actually make some real progress. At least that is my very biased view as a statistician.
But looking at your presentation, so you spoke about statistics, and then you spoke about representation of the data in various sort of persistence transform. There's the homologic transform, Euler characteristic transform. So the idea is you are really different from different angles. There is this equivalence.
Yeah.
If I ask you to tell me in 1 minute why it pays off to move from whatever data you have into topology and do your statistical stuff on that side, what would be the answer?
So the idea is, yeah. His question is, why are you doing all this topology nonsense? right? Like, why not take the data and just try some model, do something, right? Like, looks like you can do stats. Why are you doing all of this nonsense, right? Is that fair? So the problem is statistical modeling without coordinates is really hard, right? And the question is, especially in the case where I don't have diffeomorphisms, is there something that I can move into that looks kind of coordinate free, right? I mean, it really does have coordinates at the end of the day, but it doesn't explicitly have them, right? And that's the argument for using these going in a direction and looking at these summaries. In a way, they're all, they're aligned in a way, right? And I can use that structure and that local linearity, right, to push things forward. So that's the argument. You could have done something else. If you have enough data, you can run it through a deep neural network, and with some possibility, you'll be fine.
Non-zero possibility.
Non-zero.
So, yeah. Okay, you're optimist.
So that's why. One thing that we did that we failed at is we wanted to use similar ideas for graphs to represent graphs. Yeah, you have different graphs. And then what I was going to do is take the graph Laplacian, filter according to those, right? Those were my notions of directions, to get a bunch of Euler curves, right? And then use this to do similarities. And it did not work.
There are different methods of vectorizing graphs.
Yeah. That didn't work. What could have been also there was a bug in it. We tried it.
So you use Laplacian to get what?
So you use a Laplacian to get eigenfunctions, and then basically that's like your height function. You filter in those directions, right? And then you look at the height according to those directions.
So the first eigenfunction should give you the bottlenecks, right?
Yes.
So we put the bottlenecks first, and then the rest shouldn't be doing
Maybe it's the other way.
the other way
Or
around.
maybe the other way.
Just asking.
With the same spectrum.
Yeah.
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 That's-
Yeah. You have that problem of the drum.
yeah,
Can you hear the shape of the drum?
okay.
The answer is no. So the other thing is the persistent homology transform is functorial for people who care about that. The persistent homology transform does not have a nice inner product space for other people who care about that. And it probably really depends on what you're trying to do in terms of when you want one versus the other. I would argue in most statistical applications, having an inner product space is more important than being functorial. I guess we can stop a little early then.
Stop the recording.